All right. Good afternoon, everyone. Thank you for joining us today for our summer paper presentation. My name is Sun Nguyen, and I'm working with Professor Teja. And over the past few months, we've been working on human AI collaboration with some companies. And then during that time, we noticed some gap between how do you adapt the object detection deep learning model into businesses, and they tend to, and then we noticed the gap for small object detection, so they're not performing well on them. I'll present this dynamic tiling efficient uniform patching solution for small object detection. The work have been presented as SCCR 2023 and got accepted to present at workshop on data science at Informs in October. So here's, I'll go over motivation and research question, some related work, methodology, results, and summary. So as you know, object detection model is fundamental in a lot of applications from autonomous vehicle to medical imaging. As you can see here, however, object detection models face significant challenges when detecting extremely small objects relative to the image size. So it's performing well on closer object, but for further smaller objects, it couldn't able to do it. So prior research recommends some alternative strategies. For example, just use a high resolution image or modify network architectures, and also artificially increase the size of the image resolution via super resolution techniques. However, these techniques usually very resource intensive, time consuming, and even costly to do. So we aim to mitigate this problem by in modern object detection models. So we explore another kind of strategy called tiling. It's another approach that focusing on inference data centric and to solve the small object detection problem. So why is it's inference data centric? So it's using the inference data, which is the initial inference data to improve the results. So what is tiling? So it's gonna break the images into different small patches for independent object detection. Then later on, it's gonna merge those detections together to form a more comprehensive detection of the entire image. So sliding windows or overlapping often used to ensure that fragmented objects that are caused by the tiling process can be combined together. So advantages of tiling is boost for proportional pixel coverage of smaller objects relatively to the full image. And it's make it easier for the model to actually detect objects, because the model only need to focus on a small area at a time. And also it's allowed for the model to utilize the whole resolution image, the whole resolution of the image, even though you have limited GPU memory. However, this technique needs further optimization in accuracy and efficiency to enhance its effectiveness in practice. So our research, our work aim to achieve disparate size object detection by crafting efficient tiling solution for inference. Our focus is improving efficiency as well as accuracy while being mostly model agnostic. So here,
I just want to make sure I fully appreciate the research question. So if I don't work in the space, but if I was thinking about how to design a model to detect really small images in a picture, what I might do is like first build maybe one model that just figures out the regions to look at more carefully, and then build a second model to then just like zoom that out and then just do your normal image recognition on those smaller regions. Why is that either inefficient or have low accuracy? What's the issue with something like that?
There's some research on that, which is identify which regions is have high density kind of thing, and then just zoom in on it. But you need to have another model on top of your model to see that, oh, there's gonna be this region is high density and then have high probability of having objects in there, and then zoom in. So that's gonna be the two. You need to have like another model behind after that to do that, and then.
And why is that bad?
Yeah, like that seems reasonable, like,
It's another alternative approach. It's not bad, but here we just figured out, okay, with tiling, which is that uniformly perform across the whole image. I mean, with another model, of course, you can get. I mean, it's not going to be 100% accurate, right? So for this, you perform for the entire image. So. We just want to improve the efficiency and accuracy on this type of approach.
I think the question is if that's your goal, so you are going to improve the efficiency and maybe accuracy of your model, so then you shouldn't.
While being model agnostic is the
Yeah.
last phrase in that sentence.
So it's not dependent on.
Okay.
can you elaborate on model agnostic in this context?
So we don't care about which object detection model we are using. The only assumption we have is the model have to be good enough. That's it. And then it's just off-the-shelf object detection model. We don't want to design any subsequent models or architecture that to do small object detection.
So when you say you're given a model, we should assume we have a model that given a pixel or given an image, will tell you if something is in it, but only if that something is very large relative to the size of the image? Like, what are we
Yes.
assuming about?
So here so object detection model is gonna recognize and also localize. So it's recognized, is there a car and where is that car in that image? So our current object detection model only work well on bigger objects, and they can recognize and localize bigger objects, but they're poorly on somewhat smaller objects. So. So yes, so here I come to some related work. So the DartHep YOLO V4 for YOLO V4, YOLO V4 is an object detection model, and DartHep is proposes some idea about how to do tiling. So they have predefined dimension tiling with non-overlapping. So meaning that user gonna pick a grid size, for example, 3 by 3, and then the boxes are, and then performing prediction on them. And then after that, the boxes that are close to the grid line is gonna get examined. So in order to merge them together because they are potentially fragmented. So if the boxes that are aligned and are in the same class, they gonna get merged. However, we see that there's some issue with this approach because incorrect merging can happen at the boundaries, right? So for example, if we have two objects that are relatively aligned and they have the same class, this is gonna be merged into one object, which is not what we want. And also, for example, if we have one object, but then the orientation is a little bit off and we don't have aligned boxes, then this is not gonna get merged. So which also what we don't want. And another approach, which is by Unel 2019, is using the predefined dimension with overlapping tiling. So it's really similar to the last approach, but they also have overlapping threshold and then use non-maximum suppression, which is algorithm to merge all of the boxes, overlapping boxes together. And the issue with this approach is the overlapping with fixed number of tiles increase the image size. For example, if it's 640 and then you have like 25% overlap, then you have to like adjust your image to a larger size, so potentially reducing the small object pixel coverage relative to the picture is doing inference from. And the use of MMS to merge boxes across different tiles may also cause errors. So for example, here I have two tiles with overlapping, and I have the prediction from two of those tiles, and the results maybe they may not be able to merge it well enough. So for example, like this. So, and the last one is slicing window or striking tiling. So this is Sahi. They use instead of saying that, oh, I have 3x2 grid line, they only define a batch size, for example, 640 and 640, and then just strike over the entire image to get the predictions. And they also using MMS, which is also have the issue from the last approach. And also the way they're doing tiling is they keep striking. So the image size and the batch size may not align well together. So extra adjustment of batches had to be added in order to cover those areas. So it's not very efficient. So tiling is more effective with objects that are very small and fit within individual tiles and they're overlapping. However, for large objects, it struggles with objects that are very large and span across multiple tiles. And with fixed overlapping threshold, it's going to be applied across all of the patches uniformly. This may cause this very unnecessary and not efficient for detecting varying size objects in vastly different sizes of objects and also in different camera placements. So if you change the camera placement, you have to recalibrate the overlapping again for that scenario. So therefore, we propose a novel dynamic tiling strategy, a better way to do tiling involve two key components. So first, we're gonna perform inference on non-overlapping tiles and then use the predictions of the non-overlapping tiles to on-demand create and combine additional dynamic tiles to correct the fragmented boxes. So this is the diagram of our method. So first, our input image gonna get tiled and get fit into our model in one batch to obtain the predictions. After that, all of the middle predictions of the center of the center prediction of the batch is gonna get incorporated directly into the final set prediction set because they are considered as non-fragmented boxes. For the predictions that are near the edges, we are considered as potential fragmented boxes, and then we use that to further create overlapping patches based on the predictions, right? So we just draw a bigger bounding boxes that cover all the potential fragmented boxes to fit into that neural network to obtain a non-fragmented boxes. We've not only that, we noticed that because we're doing the tiling this way, so that's why for dynamic patches that can be fit together into one image, which is the model size, we can combine them together as well. So to have less full passes going through our model to further increase efficiency. After that, we know, because we noticed with tiling, we cutting out the images, so the bigger objects may not be recognized well enough because they don't have enough context to work with. That's why we just eliminate all of the big boxes and only include all the small boxes into our final set. And for bigger size objects, we're gonna get the inference from the full image, right? So, and then just get the boxes from the big boxes only from the full image, and then include that into our final prediction here. So overall, we cover all of the cases. And here is some illustrative example. Go ahead.
Yeah, so can you, yeah. So in this one, I see that the initial images has all the figures separated. So which means like, okay, there is possibility that in the end, using your method, you can get separate tiles for each and every figure. So if there is an image which contains, for example, you showed the traffic and there are cars. So in image itself, multiple objects are overlapped. So how do you saturate those? How do you separate those? And
So you mean that multiple objects in
so
the,
for example, here, let's say you put
Okay.
car over the planes figure, then would you be able to perform that well?
yeah, so if that, so that question is related to the model performance. There's gonna be some model that will be able to perform occluded object detection, so they will be able to do it. So what we have is like a general pipeline for recognizing small objects, disparate size objects. But there are models out there that can recognize occluded object as well. So we can just put that here, and then it can perform well on those occluded objects as well.
Okay.
So here's illustrative example. Here we have like a image of a street that have a lot of cars and a lot of people. And here is the route truth, which is human annotated. As you can see, with human annotated, there's also some mislabeled objects around the images. For example, there's some vehicles here that not being annotated, and on top here and there as well. So if we put the whole image into a model, here's what we're gonna get, which is also misdetect objects across the images, across the image. However, with our dynamic tiling approach, we can recognize even smaller object up there and can recognize all the vehicles down here and there. So here's Sahi, which is the previous approach. This performed relatively well, but also create some artifacts, which is not what we wanted based on their approach of merging. And here as well at Dark Help, there's some problem with this as well. So that's why their MAP, which is their how well they do on these images, is not as high as ours. So here's some quantitative results. So so we have the model type right here, model size, which is the size of the image putting into the model. FPS, which is frame per second. MAP at 50, which is how well the model perform, is similar to accuracy at IOU 50, and MAP 50 to 95, which is how well the model perform at IOU 50 to 95. So if we can build a model which is full size, we have the full size image, which is full HD, right? 1920, then we get relatively high frame per second and relatively okay MAP, which is 38.5. And for example, if we don't have that kind of resources, we have to reduce the image size into 640. Then this we're gonna get, of course, higher frame rate, and but our accuracy dropped down to 26.7. With Sahi and Dark Help, we got higher, relatively higher accuracy, but with the cost of like losing our speed. So with our approach, we are able to get the MAP at 50 to 44 here, which is relatively okay frame per second, which the smaller size model.
This is averaged over lots of photos?
Yes, this is over the entire test set.
How big is the test set?
It's 1,650 images of similar images like that.
So the density of these images do not matter here,
The
like how many objects are actually included, like I don't. So in like you said you tested like 1,000 pictures, right?
yes,
So
yes.
in terms of the density, are they like, do they have like too many objects inside or?
Yeah, so most of them gonna be similar like this. They're gonna taken over they're gonna be taken over the drone, and then they're gonna take picture. And most of them gonna have. As of right now, I do not include the data set statistics, but then it's gonna be highly dense like this. It's gonna be similar like this. Yes.
I just go back to the table, please. I think I just missed this. So you said you were comparing different method architectures based on their accuracy and time, right?
Yes.
So which of these was time?
Time is frame per second. How many frame per second?
And
The higher the better.
then map was,
The basically MAP is the average precision, median average precision at IOU 50.
higher is better?
Yeah, the higher the better.
Yeah, I mean, the definition I think is not giving, but there is some details on how to measure this for like boxes.
I'm just trying to figure out how to interpret this. So the interpretation is that yours is compared to the second highest one. So that one had the highest FPS, like 12 times higher, roughly, right? Or 11 times larger, but it had half as good on accuracy. Is that the way of
Yes,
interpreting this?
yes, that's just right.
And what is the last one
So that's,
compared to
yeah,
the 51?
yeah, the last one is the average for different IOUs.
Okay.
So IOUs is intersection over union. If the prediction is overlap 50%, then that's what we measure. If measure if it's overlap 50%, then we count. If it's not over 50%, then not count. So that's is basically how well you predict localize or recognize and localize. So that's why we're using MAP here. So this meaning that if we're doing this, so then this is like we just have to average over like a higher IOU. For example, 95, you have to overlap at least 95 in order for it to get counted as the correct prediction. So this is MAP 50 to 95. Of course, it's have lower score of compared to 50, but the industry they are mainly using 50. Yeah, but I'm included here.
So just to make sure, I just want to fully appreciate this. So what are the applications that we're interested in here? You were showing pictures of cars. Is the idea like self-driving cars? Is this, what should I be thinking about here?
Yeah, so yes, so in terms of application, yes. So for self-driving car, you can see farther away.
Good, so in self-driving cars, how fast does it need to be practically implementable?
How fast, right? Okay, I of course I haven't done this yet to actually estimate how fast do it needs to be. So, but in real time image, so for example, for cartoon, it have to be 10 to 15 frames per second in order to look like a cartoon, like a video. And for normal video or movie seeing, so it's 24 frames per second, right? So real time here is relatively depends on application, but I think for that I don't have exact answer, but we are achieving 10 frames per second with relatively low resources. So the more resources you have, the better we can get.
So I think it would make these results even more elevate them even further if you could argue that, because one of these methods is like 11 times faster, it looks like, right? And so if there was a way to sort of say that like that difference isn't important in the applications where this could be used. So
Yes.
that, because on the other hand, one could imagine perhaps that in like a self-driving car example, it needs to be doing many more frames per second in order to have the reaction time for the car to slow down and rather be fast and inaccurate. That might be more important. So like, I just want to, it would be useful to have some applications in which the regime in which because it doesn't dominate everything simultaneously. So the regimes where it does do is like an important regime.
Yes, thank you very much for that. Yes, I'll make sure I include that as well. And finally, here's some summary. So current tiling approaches are insufficient for deliberate size object detection. So we propose a dynamic tiling approach to overcome this. So it's more efficient and more accurate than competing solutions, and show how inference data centric ideas are needed well beyond just fixing or building a new architectures or need more data volume or optimization schemes for this type of problem. So future work, we would like to integrate segmentation models such as SAM, which is Segment Anything Model by Meta, 2023, and others to detect irregular shape objects as well. Not only disparate size object, but also irregular shape objects. And I think there's some preference, and thank you very much for attending